because I want to get to a different class of methods, Krylov subspace methods, that in some cases can converge faster than these methods here. There's nothing wrong with these methods here, but at least in some application we can just, we have available methods that just converge even faster, which is nice when we are handling really large-scale problems. So before getting to that, I'll spend, let's see, I'm going to spend the next 4 slides on kind of motivating these methods, but without actually talking about iterative methods. So bear with me for a few slides here. I'm going to motivate what we're going to be doing, right? Okay, so I'm going to be talking about projection methods. The idea here is that let's assume that we somehow can pick a good set of basis vectors for the regularized solution that we're trying to compute. It could be that we have information. For example, there may be certain properties of the solution that we want to capture, and we can do that by picking these columns here. So we have k columns, k vectors w1 to wk. We put them together in a matrix wk. All right. And of course, what these columns will look like, that depends on the particular application. So of course, you can't choose that without knowing about the specific problem that you're trying to solve. Anyway, assume you could do that. Well, one way to regularize then would be to say, I want a least square solution, but I know if I have no constraints on that, I'm just going to get the naive solution that I don't want. So I put the constraint that actually my solution should lie in this k-dimensional subspace there. It should be made up of those basis vectors that I have chosen, right? And the computations will then take the form that we say here, okay, we're going to write our solution there, xk, expand that in terms of these basis vectors. The coefficients in that expansion are here in the vector yk. So how do we compute that? Well, that's just the least square solution to the projected problem. This is the projected problem right there. I will give you a least square solution that satisfies this definition up there, right? All right. In fact, we've already seen something that resembles this a little bit, because if we decide that our k basis vectors here should actually be the first k right singular vectors, so v1, v2, and so on and so forth, then actually a truncated SVD solution is identical to this approach here with that particular choice. Okay, so of course we've seen it before, but now we have freedom in in choosing our w vectors, right? And in fact, maybe we can use this to our advantage, because maybe we can choose those basis vectors here in such a way that we can perform computations with them very fast. Wouldn't that be nice? So here's an example of that. So we could choose the w vectors to be samples of the cosine functions. And then multiplication with w and its transpose corresponds to doing a discrete cosine transform and the inverse discrete cosine transform. All right. So this is an example. This is a cool example because it shows that you can actually do the operations here with the matrix wk without storing the matrix wk at all. All you need to do is just plug into the MATLAB's DCT function that does a discrete cosine transform and its inverse. Right. So yeah, please study these few lines there in details to see what's going on. But the point is that this multiplication here with wk transpose is a discrete cosine transformation. So that's pretty cool. You don't even need storage for the W vectors if we decide that our W vectors are going to be the cosine basis. And another thing is that we can do these matrix vector multiplications in n log n time. So that's pretty neat. No storage requirements in fast computations. So let's take a look at that. So this is the Shaw test problem from regularization tools. The exact solution that we are trying to recover is the blue dashed line. And now in the top 8 plots, I show you the solutions computed by means of this projection method here with k equal to 1, 2, 3, 4, and so on and so forth. All right. At the bottom, I have just plotted these discrete cosine vectors there, just so you can see what they look like. And of course, they do form a spectral basis with more and more oscillations as the index increases. All right. Okay. So if we look at the top again. For k equal to 1, I only have one basis function, and that is w1, so that's a constant. So of course I can only compute a constant approximation to my solution. That's not particularly good. With k equal to 2, I compute a best least squares solution constrained to live in the space spanned by w1 and w2. So that's also going to be pretty simple. And again, that's the red line here. It's not particularly good, is it? But you can see as I increase k, as I include more and more of these cosine vectors with more and more oscillations, I'm able to actually build up more complicated approximations to my solution. And around here, k equal to 6 or maybe k equal to 7, I have enough of these cosine vectors to actually compute a pretty good reconstruction. Right there, I have the right amount of frequencies to represent that particular solution there. And all is going well, and as I increase k, things are getting better and better until, of course, at some point, I have too many. This would be like a truncated SVD. Suddenly I have too many SVD components here. I have too many cosine components. And you see the noise is coming in. The red curve here for k equal to 10 has large oscillations. They are coming from the inverted noise. So probably k equal to 9 is just the right parameter right there. Cool. So that gives us an idea that this particular projection approach can actually work. And it works very nice here because actually the true solution that I'm trying to approximate is something that has some oscillations, some bumps going up and down. So it is something that we can represent very well in the cosine basis, of course. So, of course, it works here. If we had a discontinuous solution, it wouldn't be such a great idea to approximate it by means of cosines. Anyway, yeah. Yeah, what's the next one here? Oh, I'm making a point here with, again, that the specific cosine vectors that you need to include here can be chosen such that they reflect specific properties of your solution. So it's the same approach. I'm still using the cosine basis, and I'm doing all my computations by means of the DCT and the inverse DCT. But now my test problem is Phillips, also from the regularization tools package, and that solution there, that's the black dashed line. Well, that solution happens to be symmetric around the midpoint. Right, it's a symmetric bump right there. So that gives a hint of something we can do. Okay, what we see first here, the top figures here with the red lines there, those are approximations with 1, 2, 3, 4, 5, and 6 cosine vectors. And you see there's something systematic going on there, because the solution looks exactly the same for k equal to 1 and k equal to 2. And again here for k equal to 3 and 4. And again they look the same for k equal to 5 and 6. So what's going on there? Well, every second DCT basis function is symmetric around the midpoint, and every second is anti-symmetric, whatever you call it, around here, the midpoint, right? So we have them here on the previous slide. You can see that W1 is definitely symmetric around the midpoint. W2 isn't. Okay. W3 again is symmetric around the middle. Number 4 is not. Number 5 is, and so on and so forth. All right. So to represent a solution, an exact solution that is actually symmetric around the middle, we can immediately see that we don't really need W2 and W4 and W6 and so on. We just don't need them. And of course that's what happens here when we include, here when k is equal to 2. Nothing happens because, in principle we are providing the second cosine function, W2, but we're not making use of it because it has the wrong symmetry. So to do something more intelligent for this particular solution, let's utilize the symmetry and say let's just pick the odd-numbered cosine vectors, W1, W3, WV5, because those are the ones we need, right? And then of course we have the behavior here with the blue curves there, and in a sense we're using a smaller dimension subspace to compute a pretty good approximation. Okay, so forget about the rest of the plots there. The message here is just that it's illustrating that if you have extra information about the solution you're trying to compute, you can utilize that in the choice of your basis vectors in your projection method here. Right. And for this particular, these two examples here, the cosine basis was actually a pretty good basis to work with. And then the advantage is that you can do fast computations with it. But of course it's not always a good choice. Sometimes it works, sometimes it doesn't. And the thing is, it's fixed. You decide I'm going to use these basis vectors, or I'm going to use these. Right. The SVD basis is completely different in a way, because the SVD basis is completely determined from the A matrix. You set up your A matrix, you compute the SVD. So the V vectors are determined from the A matrix, and if you set up another problem with a different A matrix, you're going to get different V vectors. So of course the basis vectors in truncated SVD, say, of course reflect the particular problem you're solving in the sense that they depend on your A matrix. So that's completely different from here, where we just choose a fixed basis, like a cosine basis. But maybe we could take that point of view one step further. See, the SVD basis knows about the A matrix. It comes from the A matrix, but it doesn't know anything about the right-hand side. Maybe we can define yet another subspace, basis vectors for a good subspace that depends both on the matrix and the right-hand side, because then it seems that, man, we are tuning this particular subspace to this particular problem we're solving, to this particular matrix, and to this particular right-hand side, right? And so that could be one way of motivating why we would like to work with a Krylov subspace such as the one here. So the Krylov subspace we're going to be focusing on here is is this guy here. This is not the typical way to introduce Krylov subspaces and iterative methods. Typically, you start with the iterative method, and then you show that actually that method corresponds to the Krylov subspace. So I'm doing things backward here. I start with the Krylov subspace, and then I'll get to the algorithm. So sorry about that. So let's define that Krylov subspace. It's spanned by these vectors here, right? My first vector is A transpose B. The next one is A transpose A times A transpose B. The third one is A transpose A squared times A transpose B, and so on. Right. I have to be a little careful when working with this subspace here when you do numerical computations, because this is not the best way. These basis vectors here, written in this form here, or you can normalize them, and then you have the p vectors here. It's kind of an ill-conditioned representation of the basis vectors. It's much better to work with the basis vectors for the Krylov subspace that are actually orthonormal. So what you can do is you could in principle run an algorithm like the one here at the bottom, which is based on modified Gram-Schmidt orthonormalization, and that creates a basis W1, W2, W3 for this Krylov subspace here. Okay, so and then you can plug that into the projection method that I talked about already. This is the scheme for computing the W vectors, and they correspond to this particular subspace up here, this Krylov subspace. Right, that depends on both A and B, so it seems that maybe this is a good idea. Right. So let's see how that works. Okay, so again, I take my test problem, and let's see, that's going to be the same problem as before. I generate these W vectors now in the Krylov subspace, and I do my projection. Right. So let's see. Sorry. Yeah, that's what we have here. Yeah. I'm jumping a little ahead here to page 19. So if you look at the bottom here, you see, again, this is a short test problem. The exact solution is the blue dashed line there. And now my projected solutions for different numbers of k are the red lines there. And again, you can see that this actually works. We're getting some basis vectors that adjust themselves just fine to this particular problem here. And we get a really good reconstruction when the dimension of our subspace is like 10, k equal to 10. And if we go beyond that, we see that the noise is coming in just as expected. This is always going to happen at some point when we're dealing with these noisy inverse problems. So it works. Right. But I want to back up a little bit here because I want to show you actually the basis vectors that we are working with in this Krylov subspace here. So here, please look at the top line with the blue lines there, and this line here, number 3, with the red lines there, and forget the other two. Okay. So what I'm showing there on top is actually basis vectors for the Krylov subspace, the 5 first basis vectors. And if you look at them, you would probably say that they look pretty much identical. They really aren't, but with this resolution in the plot, you can't see a difference. So these p's, I back up now to slide 17 here, are the ones, that's what these basis vectors look like if you simply plug into the definition here in the Krylov subspace. But it's really not a good idea. You can see we're in for a lot of numerical trouble here with rounding errors and stuff because these basis vectors, they just look too much the same, all right? Although from a mathematical point of view, they are they are linearly independent. In practice, they will be very soon linearly dependent within rounding errors. So if I apply instead this scheme here at the bottom, based on modified Gram-Schmidt, I get the red vectors that you see there. And it's just amazing that the red set of basis vectors and the blue set, they actually mathematically span the same space. But of course, you can see that the red vectors are just much better suited for numerical computations, of course. And they are indeed orthogonal. And also, you see that once again, we have this spectral property. As you increase the index here, you have more and more oscillations, just like we have seen with the SVD basis vectors and so on. So it's all very good. It's all very good. And now here's something really, really nice. Because I took a bit of time convincing you that you shouldn't work with the naive representation of the basis vectors. You'd rather do something like this here. But the thing is that it's actually possible to compute these solutions in the Krylov subspace without even forming this basis here. You don't even have to form it. There's a wonderful algorithm that just spits out these vectors implicitly lying in my Krylov subspace. Okay. See, what I want to do is I want to, that's a top equation here, I want to compute my least squares solution with the constraint that my x is in a particular subspace that I have chosen, and here it's going to be my Krylov subspace. Right, but it turns out that I don't even have to form the Krylov subspace. I can just run the CGLS algorithm. So that's on the next page. Here, that's the CGLS algorithm. I'm not going to derive this. I'm not going to explain it. I just show you that that's what it looks like. And it's very, very, very easy to implement. It's like 10 lines in MATLAB. Right, that's it. And then you have an algorithm. It's a very well-studied algorithm, and you can find many, many books that derive this method here and why it has this particular form. So here we're going to be using the CGLS algorithm as a tool. Yeah, CGLS. Why is it called CGLS? Because it's a conjugate grade algorithm specially designed for least squares problems. Why? The nice thing about running the CGLS algorithm is that it produces solutions to that equation there without specifically forming the Krylov subspace. You see, there's no Krylov subspace in there. It can just be proven that that's what's going on. So it's quite fascinating, actually. Yeah. So we have a very nice method there for using an iterative method that produces, again, this sequence of regularized solutions where, as you do more and more iterations, you include more and more components. There's a question.
Yeah, but that's for slide 18.
I'm going to be backing up. Yeah.
Can you explain what happens in the second and fourth line?
I can.
Yeah.
I'm glad you asked. Okay, here what I'm doing is I'm showing you the coefficients of these basis vectors expressed in terms of the singular, of the right singular vectors. Right. So for example, right, which one should we take? Let's take this one here. So this is W4. It has some oscillations there. And now let me express W4 in terms of my right singular vectors. Okay? I want to write that in terms of my VI vectors. There are n of those. And of course, then I need some coefficients. Right. So, and how do I compute these coefficients here so I can write that in terms of that basis? Well, since this is an orthonormal basis, I know that alpha I is the inner product of the i's basis vector, and then the function that I'm expressing here, so that would be 4 in this case here. Right. So that's what I'm plotting here. So let's return now here to W4 and the plot below it. And so these red dots that you see here are those alpha coefficients here in the expansion. And what you see here, let's see, so that's the index I here, and there's a logarithmic plot up here. So you see that actually W4 is dominated by one particular component, and that's of course the component corresponding to 1, 2, 3, 4 to the fourth singular vector. Okay, so this is not exact. It doesn't exactly look like the fourth singular vector, but it resembles it because it's dominated by that guy. And if you look over here to the previous one, you see W3 is, and W2 and W3, both of them are kind of dominated by singular vectors number 2 and 3. All right, and so on. So that's what we see there. While if we do the same thing for the stupid representation here of the basis, then you see that all these guys here are dominated by the very first singular vector. Right. So the reason why I'm glad you asked is that what this numerical experiment here shows that this is kind of a cheap way to compute approximations to your singular vectors without computing the singular value decomposition. You run this Krylov subspace method here, and then you know that your basis vectors are going to somehow resemble your SVD basis. So in a sense, when you're running this CGLS algorithm right there, you are kind of, in a very loose sense, computing approximations to your truncated SVD solutions without the SVD, so that's kind of nice. And let me back up again here to slide number 17, because it's very nice if we like the singular value decomposition, but the matrix is too big, so we don't want to compute it. Well, but we'll still like the SVD basis. Then we have this property that we get Krylov subspace basis vectors that kind of resemble the SVD basis. But in order to achieve that, we have to pick this particular Krylov subspace that you see here on top of page on top of page 17. It's for this particular choice of Krylov subspace that we have this very nice correspondence between basis vectors of this Krylov subspace and the right singular vectors. Okay, so I'm glad I actually got to make that point. Right, and the next few slides here is just an illustration of that point here. This is the gravity test problem from regularization tools, and I do more and more CGLS iterations. And then you can see the exact solution there is in the bottom right corner, and we get better and better approximations to that until eventually the noise starts to take over. And of course, in your exercises, you're going to be doing just that to convince yourself that this works. Yeah.
Just a quick question.
Yep.
When I used the conjugate gradient method before,
yes,
there was some requirements on the system matrix. Does that still apply? I think that to be positive, definite, and symmetric.
You know what? This is a very, this is just the right time to be talking about that. Okay, so very good for reminding me. Okay, I'm going to skip the next two slides here because this gets terribly technical. So I'm going to be skipping the next two slides, number 22 and 23, because they're using a lot of effort to illustrate a very small point. I'm not really going to try. If you want to see that, read it in the book. I want to get to these Krylov subspaces here, and let me answer your question there. Right. Huh? Ta-da. Oh, I see. But I want to use this one. This one is better. Right. Yeah, so let's see. Let me back up a little bit and talk just a little bit about conjugate gradients, because some of you are already familiar with that. Let's see. So the conjugate gradient method was originally designed back in the 50s, I think, for solving linear systems AX equals B, not for doing regularization, just for solving linear systems of equations. But A needs to have a particular property. A must be symmetric and positive definite. When that is true, we can use the conjugate gradient algorithm. Symmetry is easy to check. You just look at the matrix. Positive definite, well, one way of saying that is all the eigenvalues have to be non-negative. Actually positive, they have to be positive. Right. So that's harder to check. Anyway, sometimes in many applications, when you discretize a problem to put it on a computer, you know from the underlying physics or mechanics that your matrix is going to have this property here. So that's what the conjugate algorithm is doing. I'm still not going to derive that method because it's a different story. Okay, so we are more interested in least squares problems. And then we know that the least squares solution is formally identical to the solution to the normal equations. And of course you have seen this many times. And this is good news. Because that matrix there is actually symmetric and positive definite. No matter what A is, well, let's assume A has full column rank, then this matrix is going to be symmetric and positive definite. It's pretty obvious that it's symmetric because of the way that we have defined it, and it's fairly easy to check that it's also positive definite when A has full column rank. Right, so this tells us that we can just plug A transpose A and the right-hand side, A transpose B, into our conjugate gradient algorithm. And then conjugate gradient algorithms will actually converge to a least squares solution. The disadvantage of that is you work with this cross product here, A transpose A and A transpose B. And then the CGLS algorithm is I'm backing up to that on page 20. So that's a very clever way of implementing conjugate gradients applied to the normal equations without seeing the normal equations. Because if you look through this algorithm here, nowhere you'll see A transpose times A. But you will see a multiplication with A and another multiplication with A transpose. So it's a clever and more robust way of implementing conjugate gradients for the least squares problem. Right, radio. Okay, I'm moving forward here. Because I have one slide here about other Krylov subspaces. So I certainly like very much that particular Krylov subspace that corresponds to the CGLS algorithm, because it really gives basis vectors that kind of resemble the right singular vectors, and very often that's a good idea. But there certainly are other Krylov subspace methods around, And every time, people come up with a new Krylov subspace method, there's a new underlying Krylov subspace. And there's a method called GMRes, another very nice method. That's for square but non-symmetric matrices, something that conjugate gradients cannot handle. And there the corresponding Krylov subspace is written out there. That's the definition there. So B, A times B, A squared times B, and so on and so forth. And of course now, suddenly, these basis vectors here really do not resemble the SVD basis anymore. So is that good or bad? Well, it depends on the problem. There are certain examples where this basis here is even better suited than the SVD basis, but it's problem dependent. Right? You never know before you try. So it's nice to have other methods around, because if the SVD basis is not quite the right one, you could try this one here, and maybe that will work. But there's one thing here. There's one thing with GMRes that may be not such a nice idea, and that is, you see that our right-hand side B is in the definition of this Krylov subspace. So if you're working with noisy data, that means your noise is going to be present here in this Krylov subspace here. And in certain applications, and with a large noise level, it may not be so nice that actually you express your solution in a subspace that has a large noise component. So again, in some of these applications, you'd rather work with I call it a shifted Krylov subspace here, where instead of starting with B and then AB and A squared B, you start with A times B and then A squared B and so on. So it's just, shifted. You shift the basis vectors there, and there's no B anymore. Right? So that corresponds to yet another Krylov subspace method called GMRes, range restricted GMRes. And it was designed for rank deficient, inconsistent systems of equations, but actually it also has this nice property that it purges the noisy B from the basis. And in that way you can get rid of some of the noise, and that's actually very nice. Yeah. So there's a whole world of Krylov subspace methods with different properties. And some are very good for one particular set of problems, and some are suited for a different set of problems, and so on and so forth. And you probably never really know until you try. Right? So you know what? I'm going to stop here. The last 6 slides are related to computed tomography, but that's not really part of this course here. I'm going to skip those. They're still around if you want to take a look at them, but I don't want to cover them in these lectures, so I'm going to be stopping here, and then you're going to try your hands on some of these iterative methods here in the exercises. So I'm going to finish here.